Hi everyone. So in this example, we're going to be finding the equation of a plane tangent to this equation, which you might recognize as being an ellipsoid at the point -2, 1, -3. The first thing I want to point out about this problem is you already have, from a previous section, a equation for the tangent plane that uses these partial derivatives of z with respect to x and y. We're not going to be able to use that in this problem because if you try to solve for z as a function of x and y, solving for z is going to give you something that's not a function. So you'll have plus or minus square root of some value, and that's going to keep you from being able to call this a function. So we can't do that. What we're going to do instead is define some capital F function that's got three inputs, x, y, and z. And we're going to set that equal to the left-hand side of this equation. Like this. And normally in your book you would set this equal to k, but I think it's just a little bit cleaner to not have multiple equal signs on here, so I'm going to say where k is equal to 8, that's the constant that this function is equal to. So we're trying to find the equation for the plane tangent to this, and that tangent plane, so we'll say the tangent plane has a normal vector of the gradient of this function that we just defined, and that's going to be evaluated at the point x naught, y naught, z naught. So that point where that point of tangency where the tangent plane touches this ellipsoid here. So in order to solve for this, we can first solve for the gradient. So the gradient of f, remember gradient is just a vector of the partial derivatives. In this case, partial derivative with respect to x, y, and z. Relatively easy to take the partial derivative of these, so we'll get, let's see, 2x over 4, so x over 2, 8y, and then f of z is going to be, let's see, 2z over 3. Like I mentioned up above here, we need to evaluate this vector function at the point x naught, y naught, z naught. So we're going to evaluate at the point x naught, y naught, z naught. Which is this point here. So let's go ahead and do that. So gradient of f at -2, 1, 3 is going to be equal to, looks like -1, 8, and -3 will give us -2 for that. From this phrase, the tangent plane has a normal vector of this gradient at x naught, y naught, z naught. So the normal vector of our plane is going to be this ABC, so -1, 8, and -2. Okay. Continuing with the problem, we want to figure out the equation of the tangent plane. So if we plug this into the equation of a plane, that looks like this. A times x minus x naught plus b times minus y naught plus c times z minus z naught is equal to 0. That's just our general equation of a plane. We have our x naught, y naught, z naught, and we have our normal vector. So that's going to look like, let's see, -1 times x minus -1, or sorry, apologies, x minus -2. So x plus 2. Plus b, which is 8, times y minus 1 minus 2 times z minus -3, so plus c, is equal to 0. This in turn is going to give us, let's see, negative x plus 8y minus 2z, and then I'll combine all my constant terms. So it looks like I have -2, -8 will give me -10, minus 6, so -16 is equal to 0. And that's my equation for the tangent plane. This problem is also asking for the equation of the normal line on there. So the normal line is a line that is perpendicular to our ellipsoid. So what that means is it's going to have a direction vector that's the same as the normal vector of our tangent plane, and then the point on that plane is just going to be this point of tangency, -2, 1, -3. So, like I said, the normal line has a direction vector of this gradient of f evaluated at x naught, y naught, z naught, and it's going to contain the point -2, 1, -3. So, setting up our vector equation for a line, we have that our line is equal to the vector pointing to this point of tangency, or sorry, this one right here. And then we'll have our direction vector times t. So plugging everything in, we're going to get that our line is going to be equal to this vector, -2, 1, -3, plus our direction vector that we found up here. That's -1, 8, -2 times t. This is our equation for the normal line, and I just wanted to point out that you might be asked to write this line in different forms. So I went ahead and wrote this line out in both parametric and symmetric forms, just in case you need either of those. But in all of these, the direction vector is going to be this gradient of f, and the point that you're using for your x naught, y naught, z naught is going to be this -2, 1, -3. And that concludes the problem.